Okay, so have a look at page 13. This one is March 16 P22. So we'll go through this. Your particle physics questions is usually towards the end of the paper for both P1 and P2. Okay, so you normally see them there. Now, a neutron decays by emitting a beta minus particle. This is actually talking about your beta minus decay from here. All right. They tell you complete the equation below for this decay. If you're talking about beta minus particle, the neutron will decay to a proton. Is what you're seeing right over here. Okay, so you need to know what are the particles that you get. The neutron decays to a proton, 1, it decays to a beta minus particle, 0, -1, and then you also get your corresponding anti-neutrino, 0, right? So this is what I meant just now earlier. You need to memorize the decays, otherwise you won't be able to do the questions. You can have a whole question that is based on that, right? So now, state the name of the particle represented by the symbol V bar. The V is neutrino, but because you have a bar above it, it's actually referring to the anti-neutrino. Here it is referring to the electron anti-neutrino. Okay, so the one is this. Now, state the name of the class or group of particles that includes beta minus and V bar. What's the group of particles that these two belong to? They actually belong to your leptons, okay, which is basically this part in your notes. Okay, they belong to your leptons. So what is the quark structure of a neutron? I mentioned to you is up, down, down. Okay, quark structure of proton and neutron comes out quite often, so you need to remember their structure. Okay, you can either write it as UDD or you can either write it in full up, down, down. It doesn't matter which one. All right. So then after that, they ask you, state the change of the quark structure when the neutron decays. If you already know that your neutron is UDD and then it decays to proton UUD, what you can say is your down quark changes to an up quark. Okay, a down quark changes to an up quark, or UDD become UUD, whichever you like. Okay, so this one is okay, right? So we move on to the next part of the question. This one is June 16 P11 on the same page, right? So let me open it up. June 16 P11 towards the end of the question. Okay, so this one here, they tell you which statement describes beta minus decay in terms of the simple quark model. Okay, just now we did this already, so your beta minus decay was basically this one. You can actually refer to the top part of your notes if you want to, top part of your question just now. This one is talking about beta minus decay, right? Up, down, down, change to up, up, down, down quark, change to an up quark, right? So here they ask you, which statement describes beta minus decay in terms of a simple quark model? Yeah, actually wrote it here also already at the top. So you can see a down quark changes to an up quark and it emits an electron and an electron anti-neutrino. The answer is just A. So again, if you memorize it, you can already straight away get the answer. Okay. Then which word equation represents beta plus decay? So just now as I mentioned, beta plus is positron. Positron starts with P, so it starts with proton. proton decay to neutron, giving you your beta plus and your electron neutrino. Okay, so proton to neutron to positron, electron neutrino. Answer is just D. Okay. Now for question 40, which statement about the alpha particle scattering experiment provides evidence for the existence of the nucleus? So your answer should have been A. Okay. They want the observation, which statement tells you about the evidence for existence of your nucleus. Okay. So you know that alpha part, your nucleus is actually positively charged. And your nucleus is positively charged. All right. Then after that, nucleus is positively charged. Then after that, you know that the closer alpha particle is, the closer alpha particle is to the nucleus, the greater the repulsion, therefore greater angle of deflection. Okay, nucleus is positively charged. The closer alpha particle is to the nucleus, the greater the repulsion, therefore greater angle of deflection. So the one that kind of tells you that is answer choice A. A tiny proportion of alpha particles are deflected through large angles. And this one is actually because the alpha particles, this is due to alpha particle getting too close to a nucleus. Okay. Slower alpha particles are deflected through larger angles. This one doesn't tell me anything about the existence of the nucleus. Kinetic energies of the deflected alpha particles are unchanged. This one doesn't tell me anything. Number of alpha particles deflected depends on the thickness of the fall. It doesn't really tell me anything. This remaining three doesn't tell me anything sensible. Okay, so only A is sensible. A tiny proportion of your alpha particles are deflected through large angles. This is due to the fact your alpha particle got too close to the nucleus. Okay. Okay, so this one is okay. Then you go on to page 14. Okay, page 14. This one is June 16 P12. Question 38. Okay, now gold nucleus Aurum 18579 undergoes alpha decay. What are the nucleon number and proton number of the nucleus formed by this decay? So you started off with Aurum 18579. You decay by alpha particle emission alpha 42. What is your resulting nucleus? So this one is where you have to use the conservation of proton number and nucleon number. Okay, so you notice that if I look at the proton number itself, this one is 79. So this one I will need to take 79 minus 2 to give me 77. Then my nucleon number is 185. Then this one is 4, right? So this one will be 185 minus 4. Okay. The reasoning is because of something like this now. This one is just, I think I'll show you once now. If I tell you proton number conserved, it'll be 79 equals to Z plus 2. Okay. This one is Z plus 2. Okay. Z plus 2. So Z is 79 minus 2. If I tell you nucleon number is conserved, this one will be 185 equals to A plus 4. So A is 185 minus 4. Okay, that's why I get this. This is 185 minus 4, this one is 79.2. Okay, I can just probably just write it as this. If let's just say I assume X is actually having a nucleon number of ZA and then proton number of Z, this is my full working. Okay. But usually you don't need to write until that level. I mean, if you do your questions frequently enough, you will notice that whatever is here is actually the difference between these two here. Okay, so your resulting nucleus is 181 nucleon number, 77 proton number. Okay. Now, which row gives you the correct classifications of protons, electrons, and neutrinos? So this one, if you remember just now what we went through in the notes, electrons and neutrinos are leptons. Protons, because they have quarks combined together, up, up, down, this is hadron. So answer is B. Okay, so nothing really that difficult here. So which equation represents beta plus decay? Same thing again, just like before. Beta plus decay. I always start with this now. Beta plus is positron. So it starts with P. It therefore must be proton. Okay. Proton will decay to neutron, giving me positron. And then because this one is antimatter, the neutrino must be matter. So answer is D. Okay. It won't be C because you see this one, positron is antimatter. Antineutrino is also antimatter. So just like I mentioned to you, you can see a pattern there usually. It's always matter and antimatter pair, regardless of whether it's beta plus or beta minus decay. If you see one is antimatter, the corresponding neutrino must be antimatter. If you see the beta particle is matter, then the neutrino must be antimatter. All right. So basically, that's for this one. Right. So this one is okay. So move on to some other one. So this one will get progressively harder. Okay, June 16 P13, next page. June 16 P13. Okay. The questions will not be required. Okay. Now you have a nitrogen 13 nucleus and 13-7 that undergoes beta decay. In the equations below, V and V bar represent a neutrino and antineutrino respectively, and gamma represents a photon and gamma radiation. Which equation represents this decay? Okay, so they tell you beta decay here. The beta decay can be beta plus or beta minus. They never told you whether it's beta plus or beta minus. They just say it's beta decay. So it could have been either one. All right. So they want you to find out which one represents this decay. Okay. So from here, I can actually just very quickly write out your beta minus decay. Neutron 0, sorry. you can see from here. I mean, it's easier to see once you have written down your beta minus and beta plus. This one is 0, 1. This one is proton 1, 1. Plus with beta minus 0, anti-neutrino. So beta plus decay, positron, so start with positron 1, 1 and 0, 1 plus with beta plus 0 plus with neutrino. Okay, so this is your beta minus decay, this is your beta plus decay. So you look at the equations one by one. If you just look at, say, A, this one is beta minus, and then after that you have your anti-neutrino. See, it is seemingly correct here, but then this is not what we want also, because you see the proton number is not balanced. You see this one is going to be -1, this is 0, 0, 0. Gamma radiation is just a EM wave. There's no proton or nucleon number to consider. This one you can also think of it as 0, 0 lah. Okay, so now you try to add this thing up, you will see that your proton number is not balanced. Okay, this one you can see it is all 13, which is what you have here. But when you want to look at the proton number, this one is 6 minus 1, giving you 5. This one is supposed to be 7. Okay, your proton number is not balanced here. So A is out. Okay. Then you look at B and C. The thing that is wrong with it is this one is beta minus, this one is neutrino. You're supposed to have anti-neutrino. Okay, remember I mentioned to you the matter anti-matter pair. Okay, if you have one of the beta particles, one is matter, the neutrino must be antimatter. If the beta particle is antimatter, then the neutrino must be matter. Okay, so this one is definitely out. Okay, because this is beta minus particle, it should be anti-neutrino. So you look at C, C will also be out because you see this one is positron. Positron should be having neutrino, antimatter and matter. This one is antimatter, antimatter. They're the wrong pair. Okay, so C and D is out. Then you look at the last one. D by process of elimination should be the correct one, but we can try and check from here. Beta plus particle, it has neutrino, so this one is antimatter, this one is matter, so everything checks out. But what if, let's just say right now we go and try and check whether the proton number and nucleon number are conserved. So we can check it by looking at this. Beta plus is 1 plus 1 for proton number and then 0 for nucleon number. This is 0, 0. So you add them all up. This one is going to be 7. The top one, you add it all up, it's going to be 13, which is what you have here. So this one is definitely correct. So answer is D. Okay, so that one is okay. Okay, so then after that, we go on to 39, question 39. Radon 22286 is the start of a decay change that forms bismuth 21483 by alpha and beta emission. For the decay of each nucleus of radon, how many alpha particles and beta minus particles are emitted? Right? So this one, you have to kind of like do trial and error here. So let me just clear off everything. Okay, so this one, they tell you radon will decay to bismuth by alpha and beta minus emission. Okay, So the easy way to do this one is to start off with your equation. Radon 22286, it decays into an unknown number of alpha particle and an unknown number of beta minus particle, and finally your bismuth 21483. Okay, so this one is beta minus 10. This is alpha 42. Okay. So what you can do here is basically you do trial and error. Okay, what you need to do here is you need to do trial and error for each and every one of this. And then see whether the protons and neutron numbers are balanced. Eventually you see if for A, proton number is not balanced. What I mean by that is that you can actually see from here now. If you sub in the values one by one, this one is 1, this one is 1. So how much is your proton number after the equation, after the balancing, after you sub in the values? This one is 2, this one is minus 1. So this one is 84. So 2 minus 1 is 1, 1 plus 83 is 84. See, proton number is not balanced for A. So I don't need to do nuclear number anymore, because I already know proton number is out. So what if I put it as 2 alpha particle and 1 beta minus particle? So the proton number would be 2 times 2 is 4, 1 times -1 is 1, -1. So 4 minus 1 is 3, 3 plus 83 is 86. Okay, so you see 86 here, 86 here. Okay, this seems promising. Then you go on to nuclear number, see whether they balance off. This one is 4 times 2 is 8. This one is 0. So 8 plus 214, you want to get 2, 2, 2. Okay, so this one should be the correct one. Okay, so you try to do this for C and D also, eventually you find out that they don't tally at some point or another. For C, proton number is not balanced. For D, nuclear number is not balanced. Okay, so as you try and do this by trial and error, you notice that A is definitely out, B, C is definitely out, D is definitely out. You must have a case where both proton and nuclear number are balanced, which in this case is only for B. Okay, this one was for A. So A is out. B is correct. C and D I don't want to do lah, because I already know it's wrong. But you can do this as something like extra practice later on. Okay. Right. So 40. The magnitude of the charge on proton may be represented as +1 unit. On this basis, the charges of up, down quark and the anti-quarks, U bar and D bar, are not whole units. Which row in the table shows the correct values for the charges U, D, and which row in the table shows the correct values for the charges on U, D, U bar, and D bar quarks? Okay, so remember one of the first thing I mentioned to you just now is that quarks, antimatter or antiparticles would always have opposite charges to the equivalent matter. Okay, here I wrote antiquarks have same but opposite charges to their equivalent quarks. Same here means same magnitude. Okay, but I think it's enough to just say opposite charges now. No need to write same now. Okay, antiquarks have opposite charges, equal but opposite charges. Okay, maybe it's better to write this now. Antiquarks have equal but opposite charges to their equivalent quarks. Okay, because this one antiquark is antimatter, quarks is matter. So one of the first thing you would have learned just now by looking at the table, just now I asked you that, mentioned to you, you need to memorize the table, right? So up quark is plus 2 over 3e, down quark is negative 1 over 3e. So if up quark, if we are talking about matter, up quark is plus 2 over 3e, down quark is negative 1 over 3e. The antimatter U bar and D bar would be opposite charge, no? Negative 2 over 3e, positive 1 over 3e. Okay, so your answer would be answer choice C. All right, so this one would be your answer just by remembering what is an antimatter. Okay, yeah, one thing I should probably mention to you also is that now from this table, when it comes to the questions that are asked in your exam, most of the time they tend to center only on this one only. Okay, most of your exam questions till now, they only center on this part of your table. The remainder part of your table, which is this one, very, very seldom. Most of the time is on this part. So it may not be as complicated as you think, where you need to memorize the whole table. You really only need to memorize this section that I circled here, because most of your questions are from there. All right. Okay, so this one is okay. Then we move on to next one, June 16 P21. Okay. Give one example of a hadron and a lepton. Okay. So hadron is just your proton and neutron. Hadron is groups of quarks, as I mentioned. It's either your proton or your neutron. Okay. A lepton is basically your electron or a neutrino. Okay, so these two are the most common ones. Just give the common ones and you should be fine. All right. So that one's okay. Now describe in terms of a simple quark model, a proton. This one is up, up, down, or UUD. A neutron is up, down, down, or UDD. That's all there is to it. So no, this one, no issues here. Okay, so this one is okay. Now, beta particles may be emitted during the decay of an unstable nucleus of an atom. The emission of a beta particle is due to the decay of a neutron. This one, they already tell you what to start from. Okay, complete the following word equation for particles produced in this reaction. Okay, they tell you the emission of beta particle is due to decay of a neutron. This one is talking about beta minus decay. They never really told you whether it's beta plus or beta minus. Notice that? They just say that it is due to the decay of a neutron. If you see here, it's due to the decay of a neutron, you already know it is beta minus decay. All right. So neutron change to proton plus electron plus anti-neutrino. Okay. Here, if you want to write electron anti-neutrino, is fine. A lot of times in the marking scheme, if you just write anti-neutrino, this one is fine. But if you want to write electron anti-neutrino as the full form, it's also fine. Usually, they don't really need you to write the term electron inside. If you just write anti-neutrino, it's fine. Okay. Right. So state the change in quark composition of the particles during the reaction. This one shouldn't be an issue. Up, down, down, change to up, up, down. Up, down, down quark, change to up, down, down quark. Or you can just simplify your workings. Down quark, change to up quark. That's all that is to it. Right. So this one, no issues, very simple. So clear off everything here. Then after that, move on to where is the question? Okay, this one is okay. Right, then they start to make it a bit complicated. Okay, June 16 P22, question 8. Right, state the name of the class or groups to which the following belong. Electron belongs to lepton, neutron belongs to hadron, neutrino belongs to lepton, proton belongs to hadron. Okay, because we know that neutron is up, down, proton is up, down. These are groups of quarks, so it's hadron. Okay, you can also say they're baryon. Okay, but baryon I didn't really cover because I didn't notice them being asked before up to now, so I'm not going to cover that. All right. You can also say it's baryon. Baryon is a very specific kind of hadron. Okay, hadron is a general name. Okay, so it's enough just to know it's hadron. Okay, now a proton may decay into a neutron together with other particles. Complete the following to give an equation that represents this proton decay. You start off with proton. So this one you know must be positron because you start off with P first. You start off with P, this one is positron. Okay, so positron decay to neutron, giving you positron, proton decay to neutron, plus positron, plus neutrino. So N10, beta 01, and then V00. Then write an equation for this decay in terms of the quark composition. In terms of quark composition, okay, when they say in terms of quark composition, you need to write it in this form. All right, so this one is U, UD, become UDD. Okay. Now, state the name of the force responsible for this decay. What is the name of the force responsible for this? Where your quark is changing to a different type. So as I mentioned to you just now in the last page of the notes, the one that is responsible for your quarks changing flavor is your weak nuclear force or your weak interaction. Okay, you don't really need to write the word nuclear if you don't want to. It's weak interaction or weak force. In the notes, I don't think I wrote nuclear there. Did I? No, I did not write that. Okay. It's your weak interaction or weak force. But here they say weak nuclear force. It's the same thing. Okay. So this one is all right. If me normally they say state the name of the force. So yeah, by right you should write force now. Okay. Yeah. So just write weak force or weak nuclear force. Both will be okay. All right. So that one is okay. Then we move on to the next question again. Okay, notice that the variation has started to change a little in terms of the things they ask for fundamental particles. Okay, next page, June 16, P23. Distinguish between alpha particle and beta plus particle. Okay, now alpha particle is this one, alpha 42. Okay, so this one, 2 proton, 2 neutron. The charge of your alpha particle is going to be plus 2e. The mass of your alpha particle is going to be 4u. But when it comes to positron, this one is your anti-electron. Okay. So the charge is going to be plus E. The mass is going to be 1 over 2000 U because anti-electron, the antiparticle of electron by right should have opposite charge but same mass. Okay, so that's why here the mass of positron is 1/2000 U. It's actually the same mass as electron. The charge is positive U because it's opposite to the charge of an electron. Okay, so any one of these things, or any one of the statements that are listed here, like any three statements, you can either say that alpha particle has 2 protons, 2 neutrons, while beta plus particle is positive electron, or alpha particle has charge of plus 2e, while beta plus particle has charge of plus e. Alpha particle has mass of 4u, while beta plus particle has mass of 1/2000 U. Alpha particle is made out of hadrons, while beta plus particle is an lepton. Okay, so this one also possible. Okay, yeah, this one I think better I just write it as this. Your alpha particle has 2 neutrons, 2 protons, maybe, so I better just rub this one off. Alpha particle has 2 neutrons, 2 protons. Okay, so this is your helium alpha particle. All right, right? It consists of 2 neutrons and 2 protons. So you see, each one of these is a hadron. Okay, neutron is a hadron, proton is a hadron. So you can say that your alpha particle is made of hadrons, while the beta plus particle itself is a lepton. Also possible. Some answers may also write it as this. In some other rare cases, you could also say that alpha particle is metal particle, while beta plus is anti-matter particle. Also somewhat okay. All right. Alpha particle is metal particle, where beta plus is antimatter particle. That one is also kind of correct. Now, state the equation that shows the decay of a particle in the nucleus that results in beta plus emission. All particles in the equation should be shown in the notation that is usually used in the representation of the nuclides. So basically show beta plus decay. Right? So beta plus positron starts with P, so it's proton. So proton decay to neutron plus positron plus neutrino. Okay. Now, sometimes you may notice I don't write the plus sign. If you don't write the plus sign and then you just write the 1, it's fine. Okay. Sometimes you may notice I write plus. Sometimes you notice I don't write the plus. It doesn't matter actually. If you don't write a plus sign, it's already automatically assumed to be positive. Okay. So this one is your correct equation. Proton become neutron plus positron plus neutrino. Okay, so that one is okay. Now state composition of proton and neutron, up, up, down, down. This one no issues here. Okay. Now the next thing you want to do is to explain the charge of a proton. This one you need to explain why the charge of a proton is plus E. So you have to write something like this. Up quark has charge plus 2/3e, while down quark has charge of -1/3e. Since proton has quark composition of UUD, therefore total charge is plus 2/3 plus 2/3 minus 1/3e, giving you plus 1e. Okay. So this one is for quark composition. Right. See, notice this one is already 8 marks. This is already the close to 1/6 of your P2 marks. Okay. Right, so this one is okay. Then I move on to the next one. Okay, so November 16 P11. This one I'm just doing things page by page now. All right. Okay, what is proton? Proton is a hadron. This one we know already. Proton is a hadron. It's up, down, down. If you see answer choice B, it's a particle consisting of 2 down quarks and 1 up quark. This is actually wrong composition. It should be 2 up quarks and 1 down quark. So this is out. Now, proton is a positive fundamental particle. The thing that's wrong about this is the fundamental part. Okay. Just now I mentioned to you that your proton is not a fundamental particle because it can be broken down into even smaller particles consisting of quarks. So the thing that's wrong about this is they say that it's a fundamental particle. Then for D is a lepton. Lepton is not a proton. This is out. So this one for B, the thing that's wrong is this one. This one should be up. This one should be down. Okay, so I think possible answer is A. So what are the correct descriptions of gamma ray and beta minus particle? So as I mentioned to you, gamma ray is EM radiation. Beta minus particle is basically your electron. So answer is the C. Right? So that one is okay. Then for 14, in a radiative decay series, 3 successive decays each result in a particle being emitted. The first decay results in the emission of beta minus particle. The second decay results in the emission of alpha particle. The third decay results in the emission of beta minus particle. Nuclei P and S are compared. Which statement is correct? Okay, you can actually make your life a lot easier. Now, the workings that I showed you here is I'm showing you the sequence of decay, the sequence of each decay from P to Q, from Q to R, from R to S. This is what I'm showing here. Okay, and also because your particles didn't have a nuclear number and proton number attached to them, I just assume that P has nuclear number A, I just assume that P has nuclear number A, proton number Z. Okay, so now I'm showing the decay one by one. PAZ, if I have beta minus decay, so this one is Z plus 1, A plus 0. Then after that, from Q, Z plus 1, A, if I decay to have alpha particle, this one will be Z plus, wait, sorry. How do I get Z minus 1 is because I have Z plus 1 minus 2 giving me Z minus 1. That's how I got this. Then this one is A minus 4. Okay. So I want this one again. R is A minus 4. Z minus 1 decay to S by emitting beta minus particle. So this one, I want to get this value here is actually Z minus 1 minus with negative 1 giving me Z. Then this one here at the top is A minus 4 minus 0 giving me A minus 4. Okay, this one. Okay. So this one here, I think I did not show for the top one. This one is just A minus 4. All right. Okay, now this one may seem a bit tedious because you're doing it step by step. You can actually do it in a better way. You see, from P to S, you know you have 2 beta minus and 1 alpha for 2. You can actually simplify your working a lot just by doing this. P is AZ decay to S plus 2 beta minus plus 1 alpha 4 2. This one will actually make your whole life a lot easier. So this one, what I'll do is z minus with -1 minus with 2. This one will give me z minus 1. Sorry, wait. Z minus 2 minus 1. Oh, sorry. I forgot to multiply by 2. Because you see this is 2, this is -1, right? Z minus with -2 minus 2. This one will just give me Z. And then the top one will be A minus 0 minus 4. I will get A minus 4. Okay? This one is actually the easier one compared to this one. This one is you're doing it step by step. So it's a bit tedious. But if you do it this way, this one is much simpler. You do it in one shot. Okay. So now once you've done this, you will notice that the new proton number is unchanged, but nucleon number is changed. This one you notice that proton number unchanged, but nucleon number change. Therefore, they are isotopes. Therefore, your answer is this. No? P and S are isotopes of the same element. Okay, right? So this one is all right. Then we move on to some other question. Okay, the variation is starting to change a little. Okay, November 16 P12. Next question. This one is 39. Okay, so I'll just clear off whatever I have here. Okay, calcium nuclide 4220 calcium is formed by beta minus decay. What are the nucleon mass and proton? What are the nucleon number and proton number of the unstable nuclide that underwent beta minus to form the calcium nuclide? So this one is slightly different. They're not asking you what is the resulting nuclide right now. They're asking you what was the parent nuclide in the first place. So this one you have to do backwards. Okay, they tell you calcium nuclide is formed by beta minus decay. This one is actually your resulting nuclide. And it was formed through emission of beta minus decay. They want you to find out what was the unstable nuclei in the first place that underwent beta minus decay to give you the calcium nuclei. So this one is what they want. They want you to find out what is element X. So this one is pretty straightforward. Because proton number and nucleon number must be conserved in any nuclear reaction, whatever proton number you have here will be your proton number here. Whatever nucleon number you have here will be your nucleon number here. So this one is 42 plus 0, giving you 42. This one is, can't see this one. This one is 20 plus -1. This one is 19. So it's 42, 19. Answer is 0. Okay. So that one is okay. Right, so answer is C. Now you look at 40, which diagram represents the structure of an anti-neutron? Neutron we know is up, down, down. So if we have anti-neutron, it's just going to be U bar, D bar, and D bar. So answer is just A. Just like that. Okay. Nothing to it. Right, answer is A. So that one is okay. Then this one, okay. Then we move on to some other portions of the question. Okay, now this one is where you start to have the Rutherford alpha particle scattering experiment. Okay, now number 16 P21. have a look at November 16 P21. Okay, November 16 P21. Oh yeah, wait, I think I went over the time already. Sorry, I thought it was 6:30, 6:15, right? Okay, never mind. You do this as your question, as your homework, all right? So this one you just copy the answer later on from the marking scheme or whatever. I just want to go through the part C first now. Okay, sorry, I thought it was 6:30. It was supposed to be 6:15 today. For part A and part B, this one I think you have no problem. For part C, the results of the alpha particle scattering experiment provide evidence for the structure of the atom. What may be inferred from result 1, what may be inferred from result 2. If you see that the vast majority of alpha particles pass straight through the metaphor are deviated by small angles, you can just say that the mass of the atom is most of the atom is empty space, following what I wrote in the first page of your notes. If you see result 2, a very small minority of alpha particles are scattered through angles greater than 90 degrees, then you have two observations or two conclusions there. You can just say that the nucleus is positively charged and the mass is concentrated in the nucleus. It's usually like this one. It's a standard set of observation and a standard set of conclusion. Particularly when they say that your alpha particles are scattered by more than 90 degrees, it's always these two conclusions. Nucleus is positively charged and the mass is concentrated in the nucleus. Okay? So just remember what I wrote in the first page of the notes and match them to the correct observations and you should be fine.